Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. This is the sixth in a series of short videos on basic electronic circuit analysis. So far I've covered Ohm's law, Kirchhoff's current law or KCL, Kirchhoff's voltage law or KVL, Thevenin's theorem, and its companion sleight of hand, Norton's theorem. In this video, I want to cover yet another circuit analysis sleight of hand called superposition. If you find this video helpful, please click on the like and subscribe so that you will be notified when new videos come out. Now, this superposition is the art of turning off all but one voltage source and solving for circuit values. And then you move through the circuit one voltage source at a time, turning off all others except the one that you're looking at, and calculating circuit values, and then doing some accounting in the end. And in the end, you end up with the right values for all of the circuit values. Now, I'm sure that this sounds really confusing, so let's take a look at this at the whiteboard and maybe we can just unravel it. Superposition, another one of those magical sleight of hand kind of things that we can use to solve a tricky problem. Here in this particular case, we're looking at a representative problem where this would apply. You have two different voltage sources and a network in between the two of them. And you're asking the question, well, what is the voltage across R3 and what is the current through R3? But you have two different voltage sources. You could write KCL, or Kirchhoff's current law, and Kirchhoff's voltage law equations around this and solve all that simultaneously, but there is an easier way to do it. And that is using superposition. Now, for the sake of superposition, what we have to do is we have to arbitrarily decide about current direction. So we arbitrarily are going to decide that all currents that are flowing in this direction or all currents flowing in this direction are going to be positive. So anything going left to right, top to bottom are positive, and anything going right to left, bottom to top, are going to be negative currents. And the reason we have to do that is because that is how we do our bookkeeping at the end of this process. And so that's what we're going to be doing. That's how our arbitrary, that's what I decide I'm going to do in this particular case. Okay, so step one, we turn off all other voltage sources except one and solve for all of the currents in the circuit. So that means when you turn off a voltage source, that means that the voltage source is then replaced with a short. So we've turned off voltage source 2. It gets replaced with a short, and this is what we're left with. So here's our representative circuit then. We have a 10-volt voltage source here. We have a resistor here. We have a resistor here. We have a resistor out here coming back here. So as you can quickly see here, this 10 ohm resistor and this 50 ohm resistor are in parallel with one another. 25 ohm resistor is in series here. And so now what we're going to do is solve for the currents through all of these various resistors. We begin with by creating an equivalent resistance of these two, which is 10 times 50 divided by 10 plus 50, which comes out to be 8.3333, I don't want to write more, ohms. Okay, so now we have a 10 volt with a 25 ohm through an 8.33 many times 3 ohm resistor over here. Well, what's the equivalent resistance of these two? Well, that's 25 plus 8.333333, and that comes out to 33.3333 ohms. All right, so now we're down to a 10-volt source with a 33.333 many times 3 ohm resistor. Now we can calculate this current, which is 10 volts divided by the 33 point so on and so forth, which just happens to work out ever so nice to be 0.3 amps. So now we know that the current flowing here is 0.3 amps. All right, so let's put that in our matrix of stuff here. We need a matrix. So we have IR1 for the first part is going to be a plus 0.3 amps because it's flowing this way. Now, knowing this and knowing this resistance value, we can calculate this voltage here. So we have 0.3 amps flowing through a 25 ohm resistor. So that means that the voltage drop across this resistor, voltage is going to be equal to the current, which is 0.3 times the 25. So the voltage across R1, in this case, is going to be 7.5 volts. Okay, so from here to here is 7.5 volts, and we have 10 volts here. So the voltage at this point right here is going to be 10 minus the voltage drop across this, or 2.5 volts. Now we know the voltage at this point. It's the same voltage across this resistor and this resistor. So IR2 is going to be, it's flowing in this direction, left to right, so it's positive. It's 2.5 volts divided by 50 ohms, 2.5 volts divided by 50 ohms. That gives us the current through R2, which comes out to be 0.05 amps, a plus 0.05 amps. All right. Finally, IR3. IR3, we know the voltage at this point is 2.5 volts. We know the resistance is 10 ohms. So we just take this equation here and we do this, and this comes out 0.25 amps. Now it's going down, and we decided that that was positive, so plus 0.25 amps. So we got all pluses here, because everything is moving left to right or top to bottom. We got our currents. All right. So now we move on to step 2. Step 2, we turn this guy back on again, which means we get rid of this short. He's turned back on again. And we're going to disconnect this guy. So that means now we have a short across here. Now we have a different circuit to look at. We have a resistor here, resistor here. We have a voltage source, which is 12 volts. We have a resistor here, and a short over here. This is 25, this is 50, this is 10. All right, we can see these two guys are in parallel with one another. So 25 times 10 divided by 25 plus 10. Oops. Boy, everything's wanting to fall down here. Okay, 25 times 10 divided by 25 plus 10, the equivalent resistance here is 7.14256 ohms. And this is still 50 ohms. These are in series with one another. So we essentially have this here, which is 50 plus this. So this is 50, 7.14256 ohms. And this is 12 volts. So now we can calculate the current going this way, which is this voltage divided by this. So that's this current here, IR2, is equal to this voltage divided by this. And so IR2 comes out to be, believe it or not, 0.21 amps. But this is moving right to left, which makes it negative. So we're going to put this up here, 0.21. Right, if that's 0.21 amps, and it is going through 50 ohms, what is the voltage across this? If we have 50 ohms and we have this current, the voltage across R2 is going to be equal to 0.21 amps times 50, and 0.21 amps times 50 gives us 10.5 volts. Okay, so that's what's across this, 10.5 volts. Well, if this is 12 volts, and we're dropping 10.5 volts across this resistor, this voltage here, which is the VR3, VR3 is going to be equal to the 12 volts here minus the voltage drop across this, is 1.5 volts. Now we know the voltage from here to here. So we can calculate the current here. We can calculate the current here. So the current through R3 is, VR3, the voltage across it, divided by its resistance. So that's equal to 1.5 volts divided by its resistance, which is 10. So the current is 0.15 amps. Now that's going top to bottom That's R3, so that is a positive current. Now let's talk about this current over here. Again, it has the same voltage on it, 1.5 volts, but it's 25 ohms. So IR1 is 1.5 volts divided by 25 ohms. And that comes to be 0.06 amps. That's 0.06 amps, but what direction is it going? It's going right to left, so that makes it negative because that's what we decided. So minus 0.06 amps. Now we've calculated all the currents in both directions. Now we get to do our bookkeeping. Plus 0.3 amps minus 0.6 amps is a plus 0.24 amps. A plus 0.05 amps minus a 0.21 amps gives us a minus 0.16 amps. A plus 0.25 amps plus 0.15 amps gives us a plus 0.40 amps. So what that is telling us is that when everything is connected back where it originally was, just like this, R1, there is a current going through R1 in this direction of the amount 0.24 amps. There's a current going through R2 in this direction, right to left, because it's negative, remember? So there's a current going through this resistor in this direction, 0.16 amps. And there's a current going in this direction through R3, 0.40 amps. Now, think about it. We got 0.16 amps coming in from this direction to this node. We got 0.24 amps coming from this direction from this to this node from here. That means that these add together. So that means that this current, 0.24 amps, coming in from here to this node, and this current entering the node. Now I'm talking about KCL, Kirchhoff's current law. The algebraic sum of all the currents entering a node must equal 0. So we're talking about node analysis now. So 0.24 amps coming from here, 0.16 amps is entering the node from here. And this says this is exiting the node, so that is minus 0.40 amps. Does this equal 0? Well, let's see. 0.24 plus 0.16, that is 0.40 minus 0.40 equals 0. 0 equals 0. Done. Works. Superposition. It allows you to take something like this, break it apart, do your calculations, your arithmetic, your bookkeeping as it were, and come up with a final answer the current through this resistor, the current through this resistor. You can calculate all the voltages. You now know what the voltage is at A, because you can say, well, we have a 10 ohm resistor, V at A. You have a 10 ohm resistor, and you know that it has 0.4 amps going through it. So you have a 10 ohm resistor times the amperage going through it. So that means that the voltage at A is going to be 4 volts. Wow, that's pretty cool. So there you have it, the short and sweet of superposition. In all reality, who would have thought that this was a way of approaching a problem like this? Not me, that is for sure. It's just one more circuit analysis trick that we can pull out of our tool belt. Without this, solving a circuit with multiple voltage sources can get a bit unnerving. If you found this video helpful, please be sure to click on like and subscribe to the channel. In the meanwhile, thanks for watching, and until next time, toodaloots.